just putting together some help for Chapter 3 homework material. This is really when we start to get in some of the tricky calculations just based on the wording and what they're asking for here. So this question, for example, question 5, how many moles of hydrogen are in 3.06 times 10 to the minus 3 grams of glycine? And before we get too far into the calculation, just be careful that this number will be different for your question. It's a variable here. So the first thing we need to know is the molar mass of glycine, and I've got 2 carbons at 12 grams per mole. I've got 5 hydrogens at approximately 1 gram per mole, 1 nitrogen at 14 grams per mole, and then 2 oxygens at 16 grams per mole. So that is 24 plus 5 plus 14 plus 32. The molar mass of glycine is about 75 grams per mole. So now I know, right, my mass of glycine. I've got 3.06 times 10 to the minus 3 grams of glycine. And I want to find moles, right? So I know I can go from grams to moles of glycine. And then I can use the formula of glycine to go from how many moles of glycine itself to moles of hydrogen in glycine. So I've got my mass of glycine. Glycine is 75 grams for every 1 mole. So I have approximately 4.08 times 10 to the minus 5 moles of glycine. Here's where we go to the formula to see in the formula, right, I've got 5 hydrogens in every 1 glycine. So that's the next step of this calculation, is to say, okay, I've got 4.08 times 10 to the minus 5 moles of glycine, and I know in every 1 mole of glycine, the formula tells us I have 5 moles of hydrogen. So we multiply that by 5, right? Moles of glycine cancel out, and we should get something like 2.04 times 10 to the minus 4 moles of hydrogen in this many grams of glycine. Again, just be careful. This number, the starting mass, will be different for your question, but the steps would be the same. I've got 3 significant figures, right, in that number, so I should have 3 significant figures in the final answer as well. All right, question 8. I've got 4.9 kilograms of carbon dioxide are produced. How many molecules? So here, we want to go from kilograms to grams because our molar mass is grams per mole. Once I have that in grams, I can go to moles, right? And that's kilograms of CO2 to grams of CO2 to moles of CO2. And then I can use Avogadro's number to go from moles to molecules of CO2. All right, so that question or that calculation, 4.9 kilograms, right? And I know for every 1 kilogram, I've got 1,000 grams. So I'm looking at 49,000 or 4,900 grams of CO2. That's step 1. Step 2, right? Carbon dioxide. Carbon is 12, and I've got 2 oxygens that are 32, so carbon dioxide is 44 grams per mole. So I've got 44 grams per 1 mole of carbon dioxide. I've got approximately 111.36 moles of CO2. Now I can find molecules, right? 111.36 moles of CO2. Avogadro's number tells us for any 1 mole of anything, right? I need 6.02 times 10 to the 23 molecules. And so that brings me to about 6.7 times 10 to the 25 molecules of CO2. All right, question 10. I've got 10 grams of C6H12O6. We'll say this is glucose. Could be fructose as well. And I want to find the number of atoms of oxygen in there. And so for question 10, we can map that out as well. I can go from 10 grams, right? Anytime I have mass, the next step I should be thinking about is moles. So that'd be 10 grams of glucose, and that would give me moles of glucose. And then from there, I can find molecules of glucose. Or we can take one step back actually and just say moles of glucose, and that would take us directly, I think, to moles of oxygen. We get the same number either way, but I kind of like this. We can do moles of oxygen because we know how many oxygens are in the formula. And then from moles, right, we can find atoms of oxygen using Avogadro's number. So here we're going to use the molar mass. Moles to moles of oxygen, we're going to use the formula, all right, the molecular formula, and here we're going to use Avogadro number. All right, so again, a three-step question. Step one, right, 10 grams, and we could look up the molar mass of this, right, 10 grams of C6H12O6, or you could calculate it. If we look it up, we'll see that it's about 180.2 grams per 1 mole. And so I've got, like 5.549 times 10 to the minus 2 moles of glucose. Step 2, I'm going to go to the formula to see that times 10 to the minus 2 moles of glucose. We go to the formula to see that for every one molecule, right, every one molecule, we have 6 oxygens in that. So I'm going to have 6 times as much oxygen. So 6 oxygens, right, for every one of the glucose molecules. So multiply that by 6. If you couldn't tell, my kids are outside in the pool. Hopefully you can't hear too much of that noise. And that gives me 3.33 times 10 to the minus 1 moles of oxygen. Right, that's takes us to step 3 now. Step 3, Avogadro's number is the only way we can go from moles to atoms or molecules, depending on what we're looking at. Right, 1 mole of anything, 6.02 times 10 to the 23 atoms in this case. Multiplied by atoms, and I get approximately 2.00 times 10 to the 23 atoms of oxygen for question 10. Question 17 is a 3-part question. All the steps are going to be the same. And sure, we could practice finding the molar mass of all these compounds. You could also just Google it and look it up like after you practice it a few times. This is not a step you need to practice a ton. But they give us heparin. Heparin is C12H19 NO20S3, which gives us a molar mass of 593.49 grams per mole. So they give us moles of heparin and they ask for grams of heparin. So this is just going to be a one step because we know we can go from moles to grams using the molar mass. All right, so I've got 0.0551 moles. And again, just be careful. Your number might be different than mine. The steps will be the same. So moles, and we know for every 1 mole, 593.49 grams, right? So I multiply that through and I get approximately 32.7 grams of heparin that we would have in that many moles. Right, part B, same process, right? We can go and add up all these elements, or we can just go and Google that to see that the molar mass is approximately 381.38 grams per mole. The important step is to see, okay, if I've got 0.0937 moles, right, how many grams is that? Well, the molar mass is our conversion factor. The molar mass tells us for every 1 mole, right, I have to have 381.38 grams. Moles cancel out, and approximately, 35.7 grams of this drug I would have. Again, just be careful. Your starting value might be a little different than my starting value, so that number of moles might be different. The steps would be the same. We would just change that number. You're still going to multiply by the molar mass, and that would still give you the final mass. 3 sig figs, because I've got 3 significant figures in the number of moles there. All right, and part C, same as the other ones, basically, right? We go and add up all of this, see that the molar mass of fluoxetine is 309.32 grams per mole. Okay, I've got 0.0551 moles, and just be careful, right? That number could be different for you. The molar mass tells me for every 1 mole, right, I need 309.32 grams. Multiply that through for approximately 17 grams of fluoxetine that we would have for 0.0551 moles in a sample. Question 20, determine the mass in grams of 7.75 times 10 to the 21 atoms of carbon. Given that the mass of 1 mole of carbon is 12.01 grams. So this one's going to be a little bit different than the previous calculations because we're going to go the other direction. We're going to start with atoms, and we know we can go from atoms to moles using Avogadro's number. And then for moles, we can go to grams using the molar, or in this case, the atomic mass. Molar mass still would apply. And again, just be careful. This number might be different for your calculation. The steps, as I've said previously, would be the same. Oh, and this is, I think this is question 19, actually. Determine the mass in grams. 7.75 times 10 to the 21 atoms. We can convert that. We know for 6.02 times 10 to the 23 atoms, that would represent 1 mole. So I've got approximately 1.287 times 10 to the minus 2 moles of carbon. All right, 1.287 times 10 to the minus 2 moles of carbon. The molar mass tells us for every 1 mole of carbon, I need 12.01 grams. So multiply to get approximately 0.155 grams of carbon for question 19. And here's where my numbers are off. This should be question 20 right here. For question 20, I honestly was a little bit confused the first time I read this question because it asks for what quantity of hemoglobin molecules. And so I honestly thought they were asking for grams, because quantity, I thought grams. But they are actually looking for the number of hemoglobin molecules. So if you thought this question was a little bit tricky, you're not alone. I thought their wording could be a little bit more clear in what exactly they were asking. Because like I said, when I read this question the first time, I solved it for grams of hemoglobin because I just thought quantity and thought grams. So there's some things we don't need, right? We don't need how much the patient weighed, right? We don't need the molar mass in this case because they're just looking for how many molecules of hemoglobin does that represent. So it ends up being a pretty quick calculation. If I've got 7.2 times 10 to the minus 3 moles, for every 1 mole of anything, we have Avogadro's number, 6.02 times 10 to the 23 molecules. So it's just a one-step calculation, but there's kind of some distractors in there because they threw in some other information. And that would give you about 4.3 times 10 to the 21 molecules of hemoglobin. Right? This first number might be a little bit different for you, but the steps would be the same. And the last question, there was a lot of questions about concentration and molarity, and we covered in the class. So for question 22, I think this was supposed to be 22, and this is where I was off. The quantity of moles of methanol that are in 150 milliliters of a 0.210 molar solution, right? 0.210 molarity is moles per liter. And so all we really want to do is we want to multiply and find out how many moles. So I want to cancel out liters. How do I do that? By using my volume. So I've got 150 milliliters. I know for every 1,000 milliliters, I've got 1 liter. So I've got 0.150 liters. So I'm just going to simply multiply by 0.150 liters. All right, liters cancels out, and I should be left with number of moles, right? I'm left with approximately 3.15 times 10 to the minus 2 moles of methanol. So sometimes these questions can be tricky when you just look at the units, right? And so molarity, sometimes it's easier to break it up into what does molarity represent. It represents moles per liter. And at the end of the calculation, I just want to know how many moles does this represent. So I need to get rid of liters. Okay, that's where I'll bring in the volume to cancel out liters. So I'll be left with moles. If I had 1 liter of solution, yes, I would have 0.21 moles of methanol. I don't have 1 liter, right? I've got about 15% of a liter, so I'm going to have 15% of that total number of moles. So hopefully that helps for Chapter 3 homework. I know there's a lot of calculations in that, but this really is the essential material for general chemistry.